We did some practicals the other day where let's just go back to those. So now I can't. That's because that's the wrong topic booklet. Ding dong, you got it wrong. Yes, so you had a reaction where you added some zinc metal to some copper sulfate, and you were able to work out that made copper and zinc sulfate. You should have this on page 22 of your topic booklets. And we can sort of strip that reaction down to just focus on the zinc part. So the zinc starts off as zinc metal, zinc element, and it forms zinc ions. And the copper starts off as copper ions and becomes copper. And in order for zinc to become zinc 2 plus, it must have done what in terms of electrons? Lost 2 electrons. So I can put those over there. And in order for copper 2 plus to become copper, it must have gained 2 electrons, so they go on the left. And then because zinc has lost electrons, we can call that, thank you, oxidation. Oxidation's loss of electrons, reduction's gain of electrons. Okay, so we have the ability to look at an equation and break it down into 2 half equations. Half equations always contain electrons. Overall balanced equations should not contain electrons, but half equations do. Half equations telling us half of the story, which bit's oxidized and which bit's reduced. Now that's okay as far as it goes, but when we see more complicated equations, so we had sodium sulfite and potassium dichromate in the presence of sulfuric acid, making blah blah blah. Well, once we start putting multiple compounds into a reaction, it becomes much harder to pull out what's being oxidized and what's being reduced, or even to just to know what's happening full stop, aside of the fact that it went from orange to green. But it's quite hard to generate the half equations from that, and I'm not expecting you to be able to do that, not yet. So in order to be able to do that, in order to be able to look at these more complicated equations and work out what's being oxidized and what's being reduced, we're going to give you a new tool for your chemical toolkit, and the tool is called oxidation state. Okay, so oxidation state is a system. Sometimes we call it a formal system. What do we mean by formal? If I said, you're going to a dinner on Friday night and it was formal wear, what does that mean? Hey?
Dress smartly.
It's a bit more than just smartly, isn't it? What, if you said you're going to a formal dinner, what are you wearing?
Suit and a bow tie.
Bow tie? Maybe a dinner jacket? Perhaps with a cummerbund and a waistcoat? Okay. Tuxedo, if you're American, we'll just call it a dinner jacket over here. So there's a set of rules applied to what you can and what you cannot wear. That's what formal means. There's a set of rules. So oxidation state is a set of rules, unlike things like, pH and temperature. I can get a pH probe and I can stick it in a beaker and I can tell you the pH is 4.8 or whatever. You can't do that with oxidation state. It's not a real thing. There's no oxidation state probe I can stick into a beaker and say, oh yeah, the oxidation state of that is 3. That it's not like that. It's a set of rules that we're going to use to help us solve problems. It's roughly, approximately, a measure of the number of electrons involved in bonding. So if you want to think of it as anything, think of it as that. But as you'll see when we get stuck into it, that doesn't always apply. Okay, so I'm just going to have to trot out the 7 rules of oxidation state, and we'll do some examples, but ultimately you're going to have to learn these, and you're going to learn them through practice. Practice until they stick. Okay, so come in order, 7 rules, and the first rule is about elements. Well, obviously, carbon is always an element. If it's methane, it's still got carbon, the element, in it. But when I'm talking about elements, I'm talking about things in their elemental state. Okay, so carbon in its elemental state might be diamond, for example. Or we might be talking about hydrogen gas or oxygen gas or a solid lump of zinc as opposed to zinc sulfate. So that would be zinc in a compound. So when we're talking about elements, the oxidation state, and forgive me if I abbreviate it, otherwise we have to write it quite a lot. The oxidation state is always 0 for elements. Although that's kind of the simplest rule, it's often the one that's most easily forgotten, probably because it's first. So, you've learned 6 more complicated rules after that, it can get forgotten. Okay, so rule number 2 is that if we have a simple ion, the oxidation state equals the charge on the ion. So if I've got, say, Fe2 plus, the oxidation state for that is just +2. Easy. If I have S2 minus, a sulfide ion, the oxidation state for that is -2. Notice that for oxidation states like charges, they're very similar to charges in a way. Like charges, we usually put a plus sign where it's positive, rather than just saying it's 2. We'll generally say +2. In the same way you wouldn't say the charge on sodium is 1, you'd say +1. So we'd say that the oxidation state is +2. With it so far? Not too scary, I hope?
It's fine.
What?
Yeah, it's fine.
It's fine.
Fine.
Okay, rule number 3. For group 1, 2 or 3 elements in compounds, because of course if they were pure elements it would be 0. But for group 1, 2 or 3 or elements in compounds, the oxidation state is +1, +2 or +3 respectively. Which is kind of what you'd expect the charges to be anyway, right? If I write down sodium chloride, you probably don't have to think too far to realise that sodium is in group 1, so it's going to have a charge of +1. So therefore it's going to have an oxidation state of +1 as well. Okay, if I had a calcium compound, calcium carbonate, the oxidation state, of calcium, that's the oxidation state of sodium there, is +2. If I had an aluminium compound, the oxidation state of aluminium is +3. Because sodium's in group 1 and calcium's in group 2 and aluminium's in group 3. Again, just to reiterate, if I had a lump of solid aluminium, pure elemental aluminium, its oxidation state would be 0. But when it's in a compound, its oxidation state is always +3. Exactly the ion you would expect aluminium to form as a group 3 element. We okay so far?
Yeah.
Right, rule number 4 is a really, really important one, and it's probably the one we're going to practice the most. In a compound, the total of all the oxidation states adds up to 0. In a compound, the total of all oxidation states adds up to 0. So, let's go back to sodium chloride, rule number 3. Sodium's in group 1, so its oxidation state in a compound is always going to be +1. So chlorine must have an oxidation state of -1, so that +1 and -1 add up to 0. Which again shouldn't come as a massive surprise, because we know that chlorine forms the chloride ion. Because it's in group 7, it can gain 1 electron to get a full outer shell, and so Cl- is a pretty common ion for chlorine. So like rule number 2, ions always give us the oxidation state. If chlorine's got a charge of -1, then its oxidation state is -1. Another example, let's do Al2O3. So we'd say aluminium, but that's in group 3. So in compounds, the aluminium must have an oxidation state of +3.
Does it not matter if there's 2 aluminium?
It does, yes. So the total contribution of aluminium to this compound must be +6, because there's 2 of them. And then there's 3 oxygens, and the 3 oxygens must contribute -6, so everything adds up to 0. So each oxygen must be -2. Again, -2 is the charge on the oxide ion, so hopefully that doesn't come as a huge surprise. It's just that we've kind of reached that from a different direction. Another example? No, that's fine. Yes. No, I'm not going to do that. We'll come back to that. Right. Rules number 5 and 6 are special rules, and they're the first rules to have exceptions. When you're building up the oxidation state rules, rule 1 is more important than rule 2. If there's any kind of conflict, we always look at the earlier rules to decide what an oxidation state should be. So, So for rule number 5, which way around is this? Hydrogen is first. Hydrogen in compounds, again, if it was hydrogen gas on its own, pure element, oxidation state would be 0, but we're talking about hydrogen in compounds, is going to be generally +1. Now that's not always true. There is an exception to that. I'll give you the exception first. And the exception is some compounds called hydrides. So I can make a compound out of sodium and hydrogen. It's called sodium hydride. Now, if we applied all the oxidation state rules that we've got on the board here, 3, 4, and 5, we might go, okay, sodium must be +1, rule number 3. And hydrogen must be +1 as well, but then it's got to all add up to 0. +1 and +1 does not make 0, so something's got to give. rule number 4 is more important than rule number 5, so it's rule number 5 that's got to give. Hydrogen in a hydride has an oxidation state of -1. Now we're not going to work with hydrides much this year, if at all. They come up again in year 13 when we do some interesting organic reaction mechanisms with hydrides. So I'm just going to pop them in that box there, and we'll come back to those next year. But for all the other compounds that we're going to look at, hydrogen has an oxidation state of +1. So let's consider ammonia. So hydrogen, rule number 5 says hydrogen is +1. There's 3 of them, so 3 lots of +1 is +3. Rule number 4 says everything's got to add up to 0, so nitrogen must be -3. Okay, nitrogen's -3. I just mention at this stage, because there's often a habit of saying hydrogen has an oxidation state of +3. There's 3 of them, so the total contribution of hydrogen to the molecule is +3, but each hydrogen has an oxidation state of +1. It's always the oxidation state of one atom on its own that matters. Have I got another example? Oh. H2S. So again, hydrogen's +1. There's 2 of them. So a total contribution of +2. Everything's got to add up to 0. So sulfur must be -2. Did you get that right? Okay. Good. Okay. 2 left. I'm sorry this ends up as a bit of a lecture, but once we've got the 7 rules kind of laid out, then we can start to do the real work of applying and understanding them. Rule 6 is about oxygen, again in compounds. If it was O2 gas, it would be 0, but in compounds, it's going to be -2. And again, there's an exception. These compounds are called peroxides. So the simplest peroxide is hydrogen peroxide. Remember, earlier rules are more important. So rule number 5 trumps rule number 6. Rule number 5 says hydrogen is +1. There's 2 of them, so +2, and then rule number 4 says it's all got to add up to 0, so the total contribution from oxygen must be -2, but there's 2 oxygens, so each oxygen must have an oxidation state of -1. Now we are going to include peroxides in our work this year, so you're going to come across peroxides quite regularly, and they're tricky little substances. They behave in a variety of unexpected ways, so just keep in mind that they're an exception to the general rule, and we won't go too far wrong. Okay, let's go back to the standard rule then, rule number 6, oxygen is -2. Oxygen is -2. So if I want to work out the oxidation state of nitrogen here, so I can say, okay, so hydrogen is +1, rule number 5. Oxygen is -2, but there's 2 of them. So oxygen is contributing +4, sorry, -4. And everything has to add up to 0, so nitrogen must be +3. Okay. Let's have a go at H2SO4. So hydrogen, rule number 5 is +1. There's 2 of them. Sorry, 2 ones are 2. It's maths for you. Oxygen is -2, and there's 4 of them, so that contributes -8. And then sulfur is whatever is needed to make it up to 0, which is +6. Let's do a... Sorry, it's not right. Let's do a harder example. That beastie, we're going to see that quite often. In fact, you were using it in the practical last time. It's potassium dichromate. It's the bright orange stuff that looks like Lucozade. Okay, potassium in a compound. +1, because it's in group 1, and there's 2 of them, so contributing +2. Oxygen, -2, and there's 7 of them, so contributing -14. Chromium, whatever it is, but there's 2 of them as well, to make it up to 0. So the contribution must be +12. So each chromium must be +6. Okay, so this kind of calculation, and I've tried to lay it out in a fairly clear way on the board. Obviously, if you can do it in your head, do it in your head. But I just want you to see where the numbers are coming from. This kind of calculation you're going to be doing a lot of in this topic. Looking at big burly compounds and saying, okay, right, well, hydrogen's +1 and oxygen's -2, and there's 3 of those, and it's got to add up to 0, and blah, blah, blah. There's one more rule. Yes. The last rule is really an extension of rule number 2 and rule number 4. Is that right? It's where you've got a compound ion. So remember, the rule for ions is the oxidation state is the same as the ion, and the rule for compounds is the oxidation states all add up to 0. For compound ions, the oxidation states all add up to the charge on the ion. So let's imagine I have the nitrate ion, NO3-. So we can say oxygen is -2, and there's 3 of them. So oxygen is contributing -6. Nitrogen is whatever it is, but the total of all of those has to be -1, the charge on the ion. So nitrogen must be +5. Okay, let's do another one. Let's do S2O3. So oxygen again is -2, and there's 3 of them. So oxygen's contributing -6. Sulfur is contributing whatever it's contributing, but the total has to be -2 because that's the charge on the ion. So sulfur's contribution must be +4, but there's 2 of them. So each sulfur must be +2. Notice that some elements, like nitrogen and sulfur, can change their oxidation state a great deal. We'll be studying sulfur as an interesting case later in the topic. But nitrogen and sulfur are not ones that can be nailed down. They get around. Gents, let's just do exercise 1, question 1A and B. So that's some oxidation states for sulfur for part A and some oxidation states for nitrogen for part B. Right, gents, let's just run through these. Sit down, thanks. So we're only interested in the oxidation state of sulfur. Can we start at the back with you, Ben, and we'll just go around the class? Because it's an element. Yeah. SO2.
+4.
H2S. S -2. Na2SO3. John, we're up to you.
+4.
+4. Calcium sulfate. Regan.
Calcium sulfate is at +6.
HSO4- Timmy.
+6. +2.
We did come across that one, didn't we, in our working. Josh, N2. Nitrogen gas is an element. N2O4 +4. HNO3. Back to you, Ben. KNO2
+3.
+3. N2O5
+5.
NH4 plus
-3.
minus magnesium nitride, yeah, and
-2.
N2H4. Okay. So again, you get used to which elements often are oxidized and reduced, and nitrogen and sulfur are good examples of elements that can change their oxidation state readily. So if you're searching in a reaction for something which is being oxidized and reduced, nitrogen or sulfur might be a good place to start. For a bit of homework, can you have a look at exercise 2? Oh, sorry, question 2, not exercise 2. Question 2. All you have to do is go through each individual element, and then just above, you see the 3 little dots just above, the magnesium and the copper and so on. Just write, small and neat, the oxidation state of each one. So magnesium in 2 part A, magnesium would be 0 because it's an element. When you get something like copper sulfate, CuSO4, you could reach a kind of impasse because the rules don't actually help you, because copper is a transition metal, it can change its oxidation state. Sulfur, as we've just seen, can change its oxidation state. So you need to use a little bit of chemical know-how. You know that there is an ion out there called the sulfate ion. And the sulfate ion has a formula for SO4 and a charge of -2. So from that, you can work out the oxidation state of sulfur And then knowing that the sulfate ion is -2, you can work out the charge and therefore the oxidation state of the copper. So it's like you're not completely pinned down to the 7 rules. You've got a bit of chemical intuition you can use as well. Can you get that done for homework? Just that question there. Thank you.
No question.
For whenever our next lesson is.